Okay, so my name is Alex, and I am the CDO of Imagimob. And at Imagimob, we understand the motion of things and people. So what does that mean? It means that we make a software that using sensors, motion sensors like accelerometers, gyroscope, compasses, you can show motions from these sensors to our software, and you can label it. And that could be my walk, for example, if I had a sensor here, or a gesture with my hand. And if I repeat this over and over again, our system will be able to recognize and match that motion in the future and tell you what actually happened. So essentially what we do is that we connect sensors to artificial intelligence. And I'm going to tell you why this is such a good idea and why everybody should be doing that, because sensors are quite dumb. So anyone here who has worked with sensors? Maybe writing some software, building some hardware? Yeah, a lot of guys doing that. That's cool. Then you know that sensors, they generate a lot of data. So if you have a standard MEMS accelerometer, usually it tells you its interpretation of the world 10, 50, 100 times each second. And that adds up to a lot of data. Not only that, that data usually contains a lot of noise. So if I'm trying to recognize my walk, and I have a sensor on my wrist, I might walk ever so slightly different. I might bang my wrist onto my leg, creating a lot of noise. Not only that, sensors are dumb. They have no memory, and they have no interpretation of what is happening over time. They just tell you what it is seeing in that fraction of a second. So wouldn't it be good if sensors generated a lot less data, and that data had much less noise in it? And what if the sensors could understand what is happening to them? If we had this, that would mean that we don't have to transmit what the sensor is seeing all the time. And we could save a lot of battery. We could live for a year on the same battery that we're using today. Not only that, if we can make decisions, we can log things, we can remember what is happening even if we don't have a connection currently. And if a link goes down, we can still send an alarm if something important happens. So let's do that. Let's make sensor autonomous. So how do we do that? We connect sensors with artificial intelligence. And what is artificial intelligence? Artificial intelligence is just a way of taking a crazy amount of input, like the input you get from a sensor, and turning it into decisions. And the way you do that is that you look at your crazy amount of input and you look for interesting features. You extract features from your data in order to compress it into something smaller. But then you still get, over time, you have these chains of features happening. So you want to get this even more compact. You want to reduce the dimensionality into something that you can recognize. You want to turn these features into a pattern, or you want to map them into a space that you can confine and label. So for example, if I'm walking, I want the output from my sensor to get mapped into the space that I have labeled walking. And then when I see walking, I can log that. Or maybe my grandma is falling over, and I want to send an alarm because we mapped into the falling over space. So yeah, in order to do this, we start with extracting features. And the way we do this is that we look at what the accelerometer gives us, and it gives us an x, y, z value, like the 3 dimensions in space, every fraction of a second. And if something interesting happens in the X space, then we put a feature here on the X line. If something interesting happens in the Y dimension, we put a feature in the Y line. And the same goes for Z. And you get these chains of features. So we're not done there. We still need to map these features into labels telling us what is happening. And a standard way to do this, or a really popular way to do this today, is by using something called an artificial neural network. And the problem with an artificial neural network, as you can see, is that it is really complex. So it can't run on a low power device next to a sensor. It just costs too much to go from your input to your output. And what is even worse is when you want to go the other way. So the way you teach this network is that you show it a lot of example data. So if I'm teaching this my walk, I'm presenting this network sensor output of me walking over and over and over again. And then I look at my output and I see, okay, does the output say walk? Okay, if it does, fine. I'll let the network be because it obviously knows what it's doing. But if it doesn't, if there's something wrong here somewhere in the output, I tune that part. I twist it ever so slightly into the direction that it should be. But when I do that, that propagates through all the active connections in the network, changing everything here. So I have to tune it very carefully because otherwise it will forget what it learned previously. So if I'm going to teach this my walk, I might have to walk 1,000 kilometers. And that's pretty painful. So what should we do? We should listen to the sensors instead, and that's what we do at Imagimob. So if we go back to, shit. That was weird. Obviously, I shouldn't stand too close to that one. If we go back to these features, we think of these features as strums. Is that how you say? Strumming a string on a guitar. So if I get a feature in the X dimension, I play a note on the guitar. And it might sound like bo. And then I get a feature in the Y, and it might sound like ba. And then I get X and Y simultaneously, and it might go ba wa 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 wa. But maybe I want to draw a circle in space, and that would turn into an even more complex sound. It might sound something like ba wa 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 wa. And then I do another circle. It's pretty similar, but not exactly the same, but it sounds similar. Ba wa 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 wa. And as I do this over and over again, these circles will map into the sound of circles. And I can build up a statistical model telling me, okay, which parts of the sound varies? How do I confine this space? So now I can label that space. So I've reached the goal because this can be executed in a very low power device on a microprocessor right next to a sensor. And so what I want you guys to take away from this talk is that sensors and AI is a really good match. Because without AI, sensors consume a lot of electricity and they're not autonomous. They have to depend on something on the outside. So if you work with sensors, go and take some AI courses. Build cool things, and if you fail, call us. And if you succeed, call us, because then we want to hire you. Yeah, that was it. Any questions? Come on. Okay, you there. No, you.
Paid my full attention, but I kind of missed the jump from neural net to sound.
Yeah. Okay.
Could you just repeat the question before you answer?
He paid full attention, but he missed the jump from neural network into sound.
How does to connect with sensors? So the sensors play the sound, or you present the data as a sound, and then you process the sound, and that is cheap.
Okay, yeah, yeah. So I'm speaking in analogies here, because I don't want to give away all of the secrets that we're doing, for obvious reasons. But so it's so it's an analogy. So we have what we call a harmonic resonance model, and it is not a sound that we are processing. We generate a pattern from these features, but we think of the guitar is really a good analogy because we let the features live for a while, like a sound. Bo. And then we have like a microphone that are tuned to listen to certain sounds and understand the composite of a more complex sound. I don't know if you...
Let's do the demo. We'll do questions after.
Yeah? Okay, so I'm gonna show you a little demo movie, which is showing... It will show you our software in action. Can you guys see here? I'm gonna pause this. So what you see up here is features going into the system, like someone playing a guitar. And at the start of this movie, the system doesn't know anything about what it is seeing. So what I've done is that I've created 3 labels. I've called them house, heart, and walk. And then I'm gonna show my system these 3 things, and whenever I'm doing it, I'm gonna say to the system, learn, learn, learn. And eventually you'll see that it doesn't get it in the beginning, but then it does. And when it gets it, it will pop up some green text over here. It's telling you what it found. So here I am, I'm gonna start learning it, what a house looks like when I draw it into there. And this is kind of stupid because I'm talking in the video. Okay, so the system doesn't understand it yet, but it's starting to build a pattern out of what it is seeing. And now it starts to get it. And it will only get better and better. And now it's not learning anymore, it's just matching. And there we go.
Question?
Yep.
What if you vary the angle of the roof? Would it still get it?
Maybe. Okay, I'm gonna.
Yeah. If you vary the angle
If
more than
so,
5 feet.
so okay. The question is, what if I vary the angle of the roof a couple of degrees,
No, more like
15 degrees? Would it still get the house? The question or the answer is maybe. It depends on how you can set the accuracy of the algorithms, but possibly you would have to draw some more houses with a slightly different angle, and then you get another pattern for that. So you can build up a database of patterns, and you can also put a composite of patterns together to understand more complex things. Yeah?
Have you applied this technique to any other type of sensors?
The question is, have we applied this technique to any other kinds of sensors? Apart from MEMS sensors. We have tried it a little bit with sound. And we've been able to see things like drums and piano sounds. recognize that in sound. And my colleague over there, Tony, did that experiment. Yeah. Sorry? Yeah, you, yep. I'm trying to look, yeah, you. You.
But have you made a speech recognition or a speaker recognition?
No, we haven't tried that. So the question was, have we tried this on speech, to do speech recognition? And the answer is no, we haven't. We're really focused on motions. And we think that that area is big enough, but it is possible in the future that we might look into that. You over there?
How do you envision this is going to be used? Who's going to buy it from you guys, or are you going to develop? What are you going to do with it?
Okay, so how do we envision this being used? How are we gonna? Yeah, who's gonna buy this? So we have 2 commercial products right now. So this tech is going into a dog tracker called Tracy Tracker, and then you can not only position your dog, but you can actually see what it's been doing throughout the day. So if your dog is drinking, if your dog is sleeping, walking, playing, you'll be able to see that in your app. And we're doing the same thing for cats for another company called Moggy. But we have a lot of other interesting projects with other companies that I can't talk about. But we're thinking industry, health applications as well. Yep.
What kind of hardware do you need? You talked about doing either computing resources.
Yeah.
That was the main force for this.
Yeah.
What do you need to run something like that?
So the question is, what kind of hardware do we need to run this? What we need is standard MEMS sensor, like an accelerometer, and then we are using an ARM Cortex M0 core as of now, so really low power hardware, and we're not using the entire capacity of the ARM Cortex. Huh?
How many percent of the capacity of the ARM Cortex are you using?
Very good question, Tony. Well, roughly 10%, I would say, and he usually says a little bit lower, but I'm careful. It all depends on the rate of the accelerometer, of course, and how many patterns you have, and so I don't know. I still have some left of the video if you guys want to see. Yeah. Okay, so now am I still doing the houses? Doing the houses forever. Okay, now I'm teaching it the heart. And I think it starts getting it. Yeah.
What happens if you try and draw a camel?
If I try to draw, yeah, hopefully it will not recognize it, but it depends. Yeah, so enough with gestures. Now I'm gonna put the sensor in my pocket and start walking around with it. And you can note that it still knows the previous gestures that I taught it, but it doesn't match on those. So it's pretty robust. And now it starts getting my walk, and it only gets better and better.
What if you
Yes. So the question is, if if I walk in a heart shape, will it get confused?
You can teach it a heart-shaped walk.
It can actually, you can teach it the difference between your walk and my walk, for example.
So something from Monty Python.
Yeah, totally.
You should.
Did you use a gyro and accelerometer for that?
So the question is, did we use only a gyro and an accelerometer for this demo? No, just an accelerometer. So we can do better with both, and we can do better if we do sensor fusion, getting rid of gravity, but it's not needed for all the applications. And now my time is out, I think. Thank you.